If you guys see something interesting, stop me with some questions. So we're going to talk about the focus areas, faculty, what the applications are, how to do research at ASU, and what circuits jobs look like. What are the areas? So principally, most of you are going to be interested in either analog circuits or digital circuits. But we also cover these three other areas. So microelectrical mechanical systems, MEMS. These are basically, we built an integrated circuit, but it has moving parts. So if you're thinking that your electrical engineering career did not have enough mechanical engineering, this would be a great place to go look. This is where a lot of neat things are going on. So anytime I build an accelerometer, the way that I build an accelerometer is I have little levers with masses on the end. And I put that inside a circuit, and when you shake it, the levers move, and I can sense the change in electricity. These end up being how we sense the world around us. This is how we're building some medical devices. These are really cool. Emerging devices and circuits. So like I said, we're very interested in how do we tweak the silicon we're making, or how do we tweak the other semiconductor devices to get interesting things. So we propose new devices, and then after we propose a new device, that isn't very helpful, so we have to propose the circuits that actually use them. So good example here is Dr. Kozicki has some really interesting resistive RAM devices. I think he has one of the better technologies for integrating those on a chip. And so we have a group of faculty who are interested in, well, how do I take those new devices and build circuits with them? So there are people working on how do I build neural networks with them. There are people interested in building neat storage devices with them. For a little bit, I spent some time trying to build neat digital circuits with them. Lots of interesting things. In terms of taking analog and going fast, if I'm doing radio frequency and microwave ICs, I need to build really, really good analog circuits. And there's some interesting challenges that come up along the way. Any questions about the areas? So roughly we break up into those areas. So there's some Vlsi / digital faculty. Vlsi is very large scale integrated systems. Basically what happened was that we had integrated systems, then we had tens or hundreds of transistors, so we had large scale integrated systems. Then we did thousands, and it was very large scale integrated systems, and then we did millions of things, and they called that ultra Vlsi, so UVLSI, and then people went, this is getting ridiculous, just call it Vlsi. So it just means we have tons of devices in one circuit. So that's me, Dr. Cal, Dr. Chakrabarty, Dr. Ogras, Dr. Sio. In terms of analog devices, Dr. Bagkalagu, Dr. Kiai, Dr. Ozev. For emerging devices and circuits, Dr. Ali and Dr. Barnaby. For MEMS and bioengineering, Dr. Che and Dr. Blaine Christensen. And then for RF and microwave ICs, Dr. Kiai, Dr. Kitchen, Dr. Trikopoulos, and Dr. Z. He's a great guy. I can't do it. So he's new. So I think he is always interested in finding people to help with what he's doing. Like I said, circuits are very application driven. They sort of exist everywhere. So we have wireless circuits, we have power management circuits. So just the process of having a battery and getting battery power into an electronic device is a whole thing. Figuring out how to manage that. If you've ever taken your voltmeter and then put it up to a battery, you've seen that if you pull a little more current, the voltage goes down. That over time, the voltage goes down. And these are real problems when you want a solid, consistent voltage. So we build whole circuits just to have a pretend voltage source. So all that time in linear circuits where you just kept drawing that circle with a plus minus and, oh, this is really nice. You know, a lot of work just goes into having one of those. Building MEMS devices. More and more security is mattering. So there are a lot more security devices. So how do I put things to make sure, so, you know, there's the obvious just building cameras that watch what's going on, but there's also things like, hey, I need to manufacture something and I want to make sure that when it's shipped from point A to point B, somebody didn't swap it out with a subpar component. How do I secure that? Or if I build something, how do I guarantee that it's what I originally built? Or if I'm building microprocessors, how do I make sure that somebody can't take advantage of the microprocessor to steal your data? More and more airplanes and cars are just hundreds of processors with huge, huge motors. So we have to think really hard about how those go together. Satellites have tons of little computers and electronics components in them. And a lot of things in terms of biosensors are there. And I think that is a cochlear implant figure. So circuits go just about everywhere. This is one of the reasons that I sort of encourage you to pursue any interest that you really have, because it turns out that there's always a way to bend your interest back to circuits. So if you're interested in photography, right, I at one point had a project looking at computational photography. So how do we build digital circuits to do photography, right? If you really enjoy surfing, I'm sure that there's like a self-driving boat thing that would be really interesting, right? There's always a way to sort of tie it back. And so I'd encourage you to kind of go pursue your interest and circuits and try and see if you can't mix them together. In terms of courses, so our core is sort of 333 HDL, 334 circuits 1, and 335 circuits 2. 333 is sort of a weird class to make you take on the entry to circuits, right? Is you'll sit down in that class and then you write a bunch of code. And most of you are going, hey, I did not come here to be a computer programmer. And if you're taking the class with either me or Dr. Abraham, you're going, I did not come here to learn Linux. This is not fair. This is upsetting. So why do we make you take that class? Well, one, it turns out that everything has digital components in it. So you're going to need to be somewhat fluent in digital design just to be able to do that. For example, if I do an analog test chip, I might use an FPGA to test the analog test chip. So I'd have to program the FPGA to do all of that work. And even if I'm supervising that work, I still need to know kind of what's going on. The other thing is that we introduce some really basic circuit analysis techniques, right? Is how do I distinguish between a test bench and a device under test? And these are reoccurring things that come up over and over and over again in circuits, and just beginning to think that way and how do I debug things is kind of important. And of course 334 and 335 provide you all of those nice analytic methods for figuring out what do these things do from first methods. And at that point we kind of split over into the more analog courses and the more digital courses. So 433 and 523 are kind of the pillar for analog circuits, and 425 and 525 are the pillar for digital. 425 is sort of low-level digital, so how do we build digital things that work well? Why does the digital abstraction work? And then 525 is, oh no, now we have billions of these, and we have a ton of problems because we have billions of transistors. How do we deal with those problems? Similarly, 433 and 523, 433 I believe looks at more sophisticated models and amplifiers, and then 523 starts to go, oh no, we actually need to build real things, and that's hard. Because it turns out that every time I go build something, it's a little bit different each time I build it, so there's some variability. And then there are all these things that I don't want in my devices that we call parasitics that are awful to deal with. And so we have a slew of topics. 526 Vlsi architectures is actually a class on how I combine digital signal processing and Vlsi design. We talked about my 498. 598. This 598 system level design for multi-core architectures is Dr. Ogras's class, which is basically from an electrical engineering perspective, how does a multi-core architecture work? So how do I build something with multiple processors in it? 598 is, I think, Dr. Sio's Neuromorphic Computing hardware design class, which is recently we've become very interested in building computer systems that emulate how our brains work. So we call these neuromorphic systems, and they've been sort of invaluable for building modern self-driving cars, modern image recognition. I wouldn't be surprised if some of our spam filters are built on neuromorphic computing right now. And so from an electrical engineering perspective, how do I accelerate that? And I think he's answering that there. Down this middle here, I think we have some of the side topics. So we have some MEMS classes covering how that works. I think if you're interested in the MEMS track, you're probably going to want to talk to some of the MEMS faculty and see what the classes are in SEMT that have some overlap, because I suspect that there are some things there. And I think you're going to want to talk to some of the semiconductor device folks here to see if there are any fabrication classes that'll help you really understand what's going on there. I think 598 bioelectronics is either Dr. Che's class or Dr. Blaine Christensen's class, and sort of introducing you into how electrical engineering actually gets into bio. Similarly, I think you'd want to talk to either of them about what courses you might take in the other bio-oriented programs to get a more full program. High-speed serial links is the problem that if I send signals over wires and I move those signals fast enough, they don't look like shorts anymore. And that's sort of awful. The faster the signal on the wire moves, the more it looks like you're trying to just shout through the air and hope that your voice doesn't disappear. RF test is an interesting class on how do you do lab work for radio frequency design. And then switch cap is, I believe, a class on building switched capacitors. So how do I build things that generate analog values using digital parts? I am much less familiar with some of these. Analog to digital converters and sigma delta data converters are classes on ADCs. So how do I take analog values and get digital values back? If you've ever used an Arduino and then just jam thing on that analog port and then somehow got a number, those classes should answer that question. If you've ever wondered how it is that I just attach a wire to a chip and now I have a radio, that sort of answers that question, is I start to actually listen to the voltages in the air and then build digital values out of them. And that's part of how I build the middle of a radio. Communication transceiver circuit design is, well, now that we have those components, how do I send and receive over the air? Symmetric VLSI design for layout. So one thing to remember is that all VLSI devices are manufactured, which means that they have little bits of variance. So it's a class on how do I minimize the impact of variance due to manufacturing. And then another class on RF transmitters and amplifiers. So how do I transmit things at radio frequencies? Any questions about classes? Yeah.
So are all the classes in white, are those required for your graduate degree? Or are they more, for example, the digital and analog courses? Between those two, can you choose which route you want to go?
So I think the white classes are required to complete the MS in electrical engineering. I think those are the questions on the comprehensive exam to finish are based off of 425, 525, 433, and 523. I think in order to get the circuit specialization as an undergraduate, you need to take 333, 334, and 335, and then some mix of these classes. I'm not very good at administrative paperwork. I don't. Those are excellent questions for your undergraduate advisors.
And then to build off of that, what would you say is more prevalent in the business world, analog or digital designs?
So there are very large companies hiring large pools of people to do digital design. Mm-hmm. So if you're interested in working for a large corporation and working on very, very large teams, that's generally what digital is going to look like. Analog design tends to be a large number of small companies with small teams building individual things. It sort of varies. And they're more unique, yeah. So digital is often a question of how do I build a lot of stuff very quickly? And analog is often a question of how do I build something special? Okay. And there are exceptions to the rule. So Qualcomm, which is a very large processor company, actually makes most of its money on the patents that it holds on analog designs. So most phone companies have to pay Qualcomm for the privilege of making a phone. And it turns out anytime I build a digital system, I need analog components. So even just having a clock on my chip requires analog design. Getting on and off my chip requires analog design. It turns out anytime I build a memory, I need to do a little bit of analog design. So it's always there. So most digital folks know enough analog to get by. Most analog folks know enough digital to get by.
Okay, but you would say in the business world, digital design is more prevalent in the business market?
I would say so. But again, if you like analog, right, do analog. Right? This isn't quite like, is there going to be a market for finger painting? Right? You don't need to quite worry that there aren't going to be people interested. And a lot of the concepts that you might learn in analog, even if you couldn't find an analog career, would be useful in other areas of engineering. And so while you may specialize in that area, you may not eventually find a job there. You will find a job doing something related. It's certainly easier to do things that you're interested in than it is to do things you're not interested in. So unless you're really trying to get out of a small town in the middle of Nebraska, right? Like, it doesn't matter too much. Cool. Any other questions about classes? Yeah.
So are like biomedical devices primarily like analog?
I would say that for the most part, it is an analog sort of concern. Is how do I build analog models for the biological components I'm interested in? How do my sensors work fundamentally? There are still some digital things that are interesting. So how do I build digital systems that exist in that context is an interesting problem. I don't think that class is going to cover that specifically. For example, so there are kind of three ways to sense what's going on in a body. One is the sort of obvious way. I just take a wire and I put it somewhere and I go, hey, what's the voltage here, right? It turns out that's a little dangerous because you don't want to run currents through people. So there are lots of design techniques to avoid doing that. The sort of second modality that's kind of interesting is taking these MEMS devices and seeing how people move or how they interact. The third is actually chemical, is you can build devices that sort of react chemically and produce ions, and then that creates voltages. And so understanding exactly how those work and how you build them, because you want to build custom ones for every scenario, is kind of interesting. More external to the body, there's imaging problems, which is I would like to shoot EM waves into your body and then see what's going on. That's more of like an RF sort of problem. And so yeah, mastering those three devices and all those problems, because they also have manufacturing challenges associated with them. They have modeling challenges. And then bio is very interesting compared to the rest of the world, because anytime I go build something that's going to be in a human body, I have to do tons of work with the FDA to make sure that I'm even allowed to do that. And so that process is very different than if I just want to sell you a processor. Interestingly, putting processors in cars is about halfway between just selling you a processor in your phone and then putting a processor in your body, which is sort of good, right? Is you'd hope those multi-ton things that people are driving around with important electronics are almost as reliable as the electronics we'd be willing to put in our bodies. Cool. Any other questions? What are some of the big research areas? So neuromorphic computing, which is just how do we build circuits that resemble how our brain processes things, or how do we pretend to be those circuits? How do we build digital things that look like that? We're still working on Vlsi design. How do we build really, really large circuits with billions of transistors? Radiation hardened circuits is interesting. So it turns out we have this nice magnetic field around our planet protecting us from the horrible particles in outer space that want to kill us. So whenever we put electronics into outer space, they don't get that protection anymore. In fact, just going a few miles up, that protection diminishes. An easy way to think about this is that God hates capacitors, and so every now and then a voltage on your capacitor will either disappear or you'll suddenly have charge on a capacitor. And that's really irritating if the capacitor was holding a bit of information. And there are other horrible things that can happen. So for some reason, those devices age much faster in outer space, which means something that you had designed to last 7 years on Earth may only last 2 years in outer space, which is kind of a problem because it costs lots of money to throw things into outer space. So you'd like them to last a while. So we have lots of work on this. This is something that I do, Dr. Kitchen does, and Dr. Barnaby does. And there's lots of cool things there. Terahertz electronics. So the next thing after gigahertz is terahertz. So, right, you went from having gigabyte drives to terabyte drives. You went from gigahertz to terahertz. If the waves are moving really fast, it's kind of interesting. They're almost at the speed of light, in terms of the frequency, which means that they have very similar properties. They don't tend to go through walls as well, in the same way that our light doesn't go through walls for some reason. And building circuits that move that fast is kind of hard. And so there are lots of challenges there. Slightly slower things are the RF and millimeter wavecom systems. So those are more your high megahertz, gigahertz systems. Those also have challenges. And then bioelectronics. And I think I have pictures. Yeah. So the big idea behind neuromorphic computing is that sort of an energy efficiency and reliability perspective. So if I put a program on a GPU to understand what an image is, it'll cost quite a bit. And then I might be clever, and maybe there's some mapping to an FPGA that'll be a little bit more efficient. But it's still not just a little bit better than a GPU. So then I might build a custom chip. So instead of buying an FPGA or a GPU off the shelf, I go build something custom and manufacture it myself. And that'll get me another 2x or 10x, but it's still not quite enough. So if I want more, what are the tricks for getting beyond that? So instead of building custom digital circuits, maybe I build custom analog circuits, or I highly tune my digital circuits for this one place. And the idea here is that a lot of what's going on in our brain is much more energy efficient than our digital processors for the amount of information processing we do. And we want to try and capture that and use that. And we're still 3 or 4 orders of magnitude away in terms of energy efficiency. So how do we build custom things that look like that? Oops. So some of this is just looking at power efficient cognitive systems and circuits. So one of the ways that you do image understanding is you just slide a little window along the image. And you guys have probably taken something like statistics or linear algebra and learning a little bit about linear regression, right? Or at least somebody at some point made you plot lines in Excel and using the linear regression tool. So one way to think about that is if I do a lot of linear regression back to back to back, so I run linear regression into linear regression into linear regression, that's roughly what a neural network is from 10 million feet. So I have these huge networks, and I want to move them along the image and evaluate them. It requires a lot of processing, and so I want to build custom chips to do that, and I want to think about how do I efficiently organize the hardware to take care of that. One problem is, on the other hand, is how do we just build really large systems? So roughly what's happened is every 2 years we've doubled the number of transistors we have, which doesn't sound like an awful thing until you let it run for 45 years. And then that's a lot of transistors to deal with. So there are lots of us just asking really basic questions along the lines of, it used to take 10, 100 engineers to build a 1,000 transistor chip. How are we going to do a 1 billion transistor chip with the same number of people? How do we empower them to do that? So we have projects that are looking at maybe if we make the high-level design of the chip way easier, if we make it easier to decide what we should build, we can relieve some of the effort. And so we have a project sort of looking at, can we do a machine learning of computation to spec those things out? Across Vlsi, we have people interested in radiation-hardened things, low-power, high-performance circuits, ultra-low power, harsh environment circuits, high-security digital systems. So how do I make sure that you aren't able to peek at bits you're not supposed to? So you guys probably remember Specter and Meltdown were in the news, that there was some trick that would let people read passwords out of your memory without being able to actually touch that data directly. Those were all tied directly to the logic implementation of the chip and the physical design of the chip. So are there things that I can do that can prevent that from happening? There's 2 camps. One camp says that is impossible, and all I can do is make it very, very difficult. And another camp that says, oh no, I have a trick, and I'll show you. So we're still waiting to find this out. This is a very exciting time for at least digital system security. Algorithms for design automation. So one way to do less design work is to make the computer do it. And application-specific acceleration. One of the things that's happened is that we have so many transistors, we're not quite sure what to do with them anymore. So now we just build circuits for really special cases. So a while ago, this was custom MP3 engines that would just decode and encode MP3s for you so that you could listen to music. Now they're H.265 encode decode engines so that when you're watching YouTube, there's a special circuit for watching YouTube. And so building these things is somewhat hard, and figuring out how to do them quickly and well is an interesting challenge. Let's see. Yeah, so how do we deal with radiation? So some of this is a design question is, how do I build circuits that are immune? Some of it's a question of, how do I organize the PCB so that I mitigate these impacts? And some of the work here is actually launching these things into space. So I think right now a few of us have projects where we're building test chips that we're going to put into simulated environments to see how they would do in outer space. And I think our eventual goal is to turn those designs into commercial designs so that they could appear in real satellites. So Dr. Trikopoulos has these terahertz imaging systems. So the neat thing is that since the wavelength is so small, that also means the antennas can be very small, almost to the point that they can be like image sensors. So I could start to build cameras that see in the terahertz range. And he has tons of projects looking at, well, how do I build these on-chip antennas that are very tiny, right? So tiny that you need microscopes to examine them. What can I do with those terahertz images? Well, I might be able to look inside electronics to make sure that the things I've built, I could actually go look at, I think that is a piece of skin, so some sort of melanoma. Could I image a melanoma to understand what's going on there? And how do I test these circuits? So when I build them, how do I understand how they work and how do I tune them? Power efficient systems and circuits. So I think all of you probably are aware of Bluetooth. You probably have 20 or 30 Bluetooth widgets sitting all around your house doing various Bluetooth things like making noise or sensing things and talking back to you, and they all just seem to run forever. Right? I think I've charged my Bluetooth speaker maybe once in 2 months. They seem to run forever, but it's a radio, right? It's like your phone. So it turns out a lot of the tricks are, how do I build custom analog circuits for talking over very short ranges that don't use very much power? If I put something in the body, that needs to last for a very, very long time, because what I hear is it's inconvenient if they have to open you up every couple months to swap out the battery. So you also need RF circuits that are incredibly energy efficient to do that. And I think all of us would love a phone that lasts longer than a day. And part of that is just not having the Wi-Fi and the LTE modems suck up tons of power. So Dr. Z is also doing terahertz ICs. One of the thoughts are that since these are very, very small antennas, they can go on very, very small satellites. And that might help us with Earth exploration and extraplanetary exploration. I think some of the things that these have been used to do is look at the moisture in soil to understand how climate change is impacting, can we grow food in these places? And these are relatively hard to do because currently one of the best methods is you send somebody out with a stick, they jam the stick in the ground and they go, it has this much moisture. So sort of a very different view of the world. The problem is that these need to, if they're going to work in outer space is hard. And so this is one of those things where the circuit is interesting by itself, but it can be used to do really, really interesting problems. Bioelectronics, care and diagnostics for disease detection. So one of the things that you might worry about with communicable disease, beyond just detecting and healing, is preventing carriers from spreading things. So if you have massive populations with relatively poor healthcare systems, one thing you could do is quickly detect the people who are sick and isolate them so that you aren't unnecessarily treating people who aren't sick or spending a lot of time trying to figure those out. But in order to do that with very, very large populations, you need relatively simple, relatively cheap devices that can interact with phones so that you can go diagnose people. And I think she has a neat project detecting disease in India And then readout circuits for monolithically integrated in CMOS. So if I'm going to build one chip with all the sensors integrated, how do I use those in biosystems? And I think that's a picture of a rabbit, because I know she has rabbits. There's fur there. Biomedical MEMS is sort of similar. Maybe we can sort of build things that deflect based off of the movement nearby. Some of this is building custom antennas. Yeah. So what you might like to do if somebody is very sick is be able to monitor what's going on in their brain contiguously. It turns out it's kind of hard to image through our skull. And there's just something about that as a medium that makes it hard to get out electrical signals. So you're going to want to put things inside. From what I hear, people do not like holes in their skull with wires coming out. What a weird concept. So what you'd like to be able to do is remove a chunk of the skull, put a sensor in, put it back and have the skull heal over so that there's no openings, and then be able to sense what's going on. But in order to do that, they need to be very small, they need to be self-contained, they need to last forever, they need to be able to talk to the outside world, but possibly by doing that, you're going to be better able to communicate through the skull. It turns out that a lot of circuits problems are, people are incredibly unreasonable. Just sort of like your spherical cows, right, from physics. You know, if the cows weren't so unwilling to be spheres, you know. We work at some of the largest employers in Arizona. So Intel makes all those microprocessors that not only do you use in your laptops or in your Apple. They make a lot of the processors that are in servers the whole world works. So anytime you log on to Google, you're probably using an Intel processor on the other side. Anytime you buy something on Amazon, you're using an Intel processor on the other side. Raytheon Corporation, oh, missiles sounds bad. So they're a huge military contractor, so they do interesting things. They don't just make missiles. I think last time I talked to them, I was talking to radar people. Some of them do very commercially oriented projects. For example, we've been using flight control systems from the 1960s. So anytime you go to the airport, that is technology from the 1960s, making sure that the airplane lands safely and takes off safely. I don't know about you guys, but I don't think there's much anything electric from the 1960s that I still use. So Raytheon has projects trying to figure out, well, how do we fix that? Honeywell builds some really interesting sensors. So I've seen them in helicopters. They have a lot of aerospace stuff that they go into. General Dynamics is very similar to Raytheon, but in addition to doing more radar things, they have a significant focus on communication systems. So they have a lot of the contracts for building custom radios for the military. So we're actually working with them to design radios. Boeing builds airplanes. They also do military contracts. So some planes in the military are Boeing, they have a great interest. They also do satellites and satellite launch vehicles. They have a great interest in how to radiation harden things. It turns out that an airplane is high enough that it matters a little bit. And of course they have satellites, so that matters as well. IBM used to be a very, very large processor company. They still design processors. Currently, they sell very large systems. Right now, their motto is sort of software as a service. I think probably the things that you will have noticed is that they had a computer that could win Jeopardy. And so they're using that computer that could win Jeopardy to do things like help doctors and help lawyers. So they're a part of why lawyers are having a hard time right now finding work. Because it used to be that you would hire teams of 10, 20 lawyers to dig through people's emails and read them and understand what's going on and then look at case law. But you don't need them anymore because IBM built computers that'll do that for them. Freescale does some custom semi stuff. Microchip Technologies has a headquarters here. They do a lot of microcontrollers. So if you played with Arduinos, that's not their product, but they have products that are very, very similar. And then Orbital Sciences Corporation, from the name, does aerospace stuff. We work at top 50 companies. So NVIDIA, they make GPUs and they make components that go into cars. They have a big kick right now on helping with self-driving cars. Their stock took a real beating because they had a Bitcoin problem. So it turned out a lot of people were buying their GPUs to mine Bitcoins, and then the Bitcoin price fell, and then the stock fell. But interesting things. Cadence Design Systems is a company that builds design software for circuits. So a lot of us end up working at the companies that build the design automation software. Google, believe it or not, has a lot of interest in circuits. Actually, I had a good friend there who's there for a while. It turns out that if you're going to build warehouses full of computer systems, that you just start building parts of the computer system yourself. This started pretty innocently, where they would buy Intel processors, build their own motherboard, and then have a custom Northbridge that they built. And then at some point, they started building custom microprocessors to go on there as well. On the other hand, Google is pushing Android pretty heavily. And so anytime that they want to add a feature to Android, oftentimes that may want to come with, how do I design a hardware component to go with it? And so they have design teams that help with that. They have research labs that build custom circuits that go into those special products. So they had the eyeglass thing that everybody wanted to make fun of, but they had a lot of circuits people helping to build that. Intel, Qualcomm, and then Burns McDonnell, I forget what they do. I think they're a big contracting firm. Naturally, we work at a lot of, you guys end up working at a lot of these places. Broadcom is sort of similar to Qualcomm in that they have a big focus on building radios. Freescale NXP is, I think, what's left over from Motorola, as well as ON Semiconductor. Let's see, AMD is Intel's competitor, so every now and then you can get a better deal on an AMD chip because that's the way the market turned. Every now and then AMD has a really good design. Texas Instruments builds microcontrollers like Microchip, but also builds some sensors. Apple designs their own processors. It was pretty interesting recently. They dumped their GPU company and then started designing their own GPU. I forget what Silicon Labs does. There are a large number of government labs that are interested in research. So I'm coordinating with a couple on different radiation designs and different design techniques. And it turns out that those are pretty good places to work. You have a lot of job security, a lot of benefits. Most of them are immune to government shutdowns because their budgets are outside of the government nonsense. So they get paid at the beginning of the fiscal year, so they already have their pot of money to keep paying their people. And a lot of people go work at startups. Cool. Any questions, concerns, thoughts, dreams, desires, hopes? So one thing I didn't talk about, but I should have, was how you might get involved in research. There are various mechanisms here. I'm blanking on the word. What's the undergraduate research program? Fury. The best way to do Fury is actually to find the professor in advance. Tell them that you're interested in doing Fury, so that when they put the request out for a Fury candidate and you apply to it, it automatically happens. And it's not this sort of mystical thing as will it or won't it. This turns out how jobs work too, is that the easiest way to get a job is to call somebody you know and ask them to put out a request for somebody, so that when you put your name in, you just get a job. The other way to do that is to engage your professors. So if there's somebody particularly entertaining or seems to have a fun view on how things are going, you might ask them what they do for research. I talked about some of the folks, but there might be others. Certainly during my office hours, I am generally pretty lonely. I am sure other faculty are pretty lonely. And if you come and ask us about the things we're interested in, we'll talk your ear off. Some of us have funding to fund undergraduates, and then some of us have funding to convince you to stay through, graduate PhDs, so that, we have good PhD students. Capstone is another neat way to get into research, as some of the Capstone projects are research-oriented. A good way to kind of make that happen in your favor is before the Capstone class even starts, is kind of reach out to somebody saying you're thinking of putting a Capstone team together to work on a project in their area. Would they help you with a topic? You certainly don't want to end up the opposite way around of, being the last team to form and then being jammed on a random research project. So what questions do you have? Yeah.
So I'm currently interning at General Dynamics, so I do RF stuff, and I was asking one of my coworkers if he thinks it's better for me to make my pathway electromagnetics or analog circuits. And he said that a lot of technology, not just communications, is moving towards much higher frequencies, and so it might be better to do electromagnetics because that will be more of the foundation rather than the analog circuits, but you definitely need a strong understanding of the analog circuits to help build the RF components and everything. What's your take on how those two interact with each other and what classes are best to focus on? Or should I keep it kind of middle ground of electromagnetics and analog?
So this is a good example. A lot of things are systems, and they touch on a lot of different parts. Radios are a really hard system, and they touch on electromagnetics because you need to know how they move through the air. You need to know how the antenna works because it isn't as easy as just grabbing a strip of wire and then attaching it to a terminal. That generally doesn't go well, though it goes kind of well enough that I haven't had to learn antennas yet. You kind of need to know how the analog components work because that tells you what's feasible or what's infeasible. And then it turns out those analog components are going to be controlled by digital parts and processed by digital components. So you're going to want to know, well, how fast can a digital control system work? How fast can a digital signal processor work? If your underlying algorithm requires huge FFTs in order to run, it may not be feasible. And then from that perspective, you may also want to take digital signal processing classes so you understand what processing you're requesting from people. It depends on, so my inclination is always to be a systems person and then try and grab a bunch of these things and put them together. But there are people who focus very, so certainly focusing on electromagnetics and the design of antennas and building very, very solid models for propagation through different media is a great idea, and that there's certainly a place for that, and then there's certainly a place for being very, very good at building individual circuits, and certainly a place for being very, very good at algorithms or very, very good at digital components. But yeah, there's an opportunity to, when you're in school, to kind of grab all of these things in parallel and see them all at once and kind of build a systems perspective, even if you do sort of narrowly converge on one thing. So I would say, unfortunately, my answer is almost always going to be choose the thing that's really fun. If you really enjoy electromagnetics, God bless you, right? So I remember sitting down for my electromagnetics final and there were people crying in the room. And then the professor brought in donuts saying, "I'm sorry." I hope that was a unique experience, but it sounds like it's not.
No.
And then on the other hand, I really enjoy a lot of the math in electromagnetics, just divorced from having to hear people talk about it. On the other hand, analog can be really fun. Analog has a lot of little puzzles in it that are great to play with, and it's really important. It's a lot about finding your joy. And certainly you guys have the opportunity to do that because there's no requirement that you be super deep in circuits or super deep in electromagnetics. You can take a breadth of these courses in an area you're interested in and then benefit from them. And then a graduate degree is, MS program is sort of a license to do that longer. Yes?
So if you wanted to be a digital designer, would you recommend taking something like DSP or like microprocessor design?
So I think microprocessor designed to be a little more helpful than DSP, but yeah, you'd want to complement it with classes like digital signal processing, like computer architecture. So I think most of you have to take the Patterson-Hennessy class, computer organization design. I think you all call it the assembly class, because that's what you think you learn in it, but it's not what you're supposed to learn. You're supposed to learn how it works, not how to write assembly. There's another class that's supposed to follow that, where they switch the authors on the book. It's Hennessy-Patterson instead of Patterson-Hennessy. That's a good class to take. Even really basic computer science classes are pretty helpful for digital design, because it turns out that I spend a lot of my time writing computer programs that design the hardware for me, rather than designing the hardware myself. So if you have an opportunity to take a data structures and algorithms class, that's a pretty good idea. I think Dr. Ali and Dr. Hutton have this Python class. Almost every thing in circuits would benefit from Python class. So on the digital circuits side, I use Python to build stuff for me. On the analog side, I use Python to size my transistors, perform the analysis for me, make really cool figures. And it's a lot faster and a little bit easier than using the design tools as they are.
So what about something like 472 power electronics? Do you think that would be like very relevant to circuit design?
Yeah, there's certainly a part of power electronics that'll be important. Actually, one of my best friends specialized in high power electronics and circuit design, and now he works at a company where they generate different high power electronic circuits for medical devices. So one of the things, so what was the thing he was telling me about last time? So during some surgeries, they'd like to remove scar tissue. So people with mobility problems in their shoulder have a buildup of scar tissue, so you want to remove it. So the old way to do this was you take a knife and sort of try and cut it out. And that does almost as much damage and is totally useless. So then what you might do is you might go in with like a little vacuum and then try and pull it out. Turns out that causes almost damage. On the other hand, if you generate a small ball of plasma, it can burn the scar tissue directly. And then you can just suck up the plasma as it's produced and get rid of the scar tissue, and that generally works pretty well. And so that's kind of this neat marriage between high power electronics and circuits, because, well, how do I build a circuit with the right control system so that I get really fine control over what is a very, very small ball of plasma? Because you'd hate for the ball of plasma to get really big inside of somebody's shoulder. That would be a bad thing. And on the other hand, he needs to understand the high power part, because one of the problems they were seeing in their device was that as it was running, it was literally stripping metal off of the surgical devices that were nearby. And that was upsetting because those are very, very expensive medical devices. And after 2 or 3 uses, they'd have to throw away what was largely like a $50,000 piece of equipment. And so they were very interested in, how do we build interesting high power models? So yeah, if you think high power stuff is really interesting, go do that and then see how it comes back later.
Just one more question. So like comparing like these 3 pathways for circuit design, which would you suggest is the best and like the second best? So like e-mag signals and like semiconductors, like those 3.
So if I was really interested in like building things, I think semiconductor is really interesting because you actually spend a lot of time talking about how do I build these devices and how are they manufactured, and that can be really interesting. If I'm interested in building systems, DSP is kind of interesting because it's, you could start to talk about, well, how do I build a radio and get that to work? And electromagnetics sort of helps with the how do I build that radio, because radios need antennas. I spent most of my career in school just taking classes that seemed fun. So I got to graduate school, there's a class on computer graphics. I said, this has nothing to do with digital circuit design, but I'm going to take a class on computer graphics. And then 2 years later, I was designing real-time rendering accelerators for somebody. Right? It didn't, at the time, it didn't make sense how it'd connect back, and then it just did magically. And so some of it's just doing what's fun and then seeing the opportunities as they arise to peanut butter and chocolate your problems. Unfortunately, I mean, if you ask honestly what I think, I'm going to say take all the digital classes and all the computer science classes, because that's where it's at. But you guys should do what's good for you.
kind of projects are you working on now?
So the thing that's giving me ulcers is I have a test chip in like 2 months where we're building a chip to go into a beam where they shoot protons at it. And then we're going to see how it stands up to high energy particles in outer space. So we're designing some test structures to measure what those effects are, but we're also building some microprocessors that are supposed to be immune to the effects, or at least highly tolerant to the effects. I have a project looking at how do we machine understand general programs so that we could design microprocessors doing that. I have a project on how do I build really, really efficient configurable microarchitecture. So how do I do image signal processing or computational photography really well. And then I have a small project looking at accelerators for virtual reality and augmented reality. Yes?
Yeah, for your radiation hardened circuits, do you focus more on like protecting and reflecting radiation, or do you make them more resilient to radiation?
Yeah, so there's a little bit you can do. So there's some ceramic coatings you can do that mitigate by like a half, but they're not very reliable, and they're also a little bit heavy, and they're expensive. So for some reason, people want to charge us a lot of money for the nice ceramics. And we hate spending money on things. The modus operandi is, can I make it cheaper, better, faster? So a lot of the tricks, at least from the circuit perspective, are can I build a device that is naturally immune? Can I change the geometry of the device when it's manufactured so that even though it behaves the same, its physical characteristics prevent things from happening? Can I build circuits that, because of how the circuit is designed and the feedback paths, that it prevents any of the effects from mattering? From a logic perspective, can I build structures that sort of ignore errors, or at least make the errors go away? So the easiest thing you could do is just build 3 of everything. And then anytime you need an answer, ask them to vote. And if 2 out of 3 agree, that's the right answer. And then hope that you never get 2 errors at once.
Does that happen frequently, where you get 2 errors at once, or is it?
It's very, very rare.
Yeah.
And then hopefully those 2 errors are far enough apart in space that they don't impact each other. But it can happen. I think I've asked friends who do these tests a lot more than I do if they've ever seen it, and they said no. So we're assuming they don't exist, or at least the probability of their existence is super low. You can do things at the architecture level. So you could run your multiple microprocessors slightly away from each other so that they're unlikely to get errors, and then every now and then you could ask, do you guys agree what's going on? And then there are software things you could do. So you could take a program and you could have it replicate itself 3 times, and then do some extra work and then ask, did my 3 different iterations through this program have the same result? So there are things that I could do, and then what combination is the right combination is really interesting. Most of what I've been doing is logic and architecture, just because those are the easy, lazy way to do things.
Thanks.
And then we're over. If you guys need to run, but I'm happy to answer questions.
So do you think what you're currently working on, do you think that has applications with like FPGAs and the stuff like concept works?
So it turns out FPGAs do really, really bad in outer space. Part of the problem is that, there's some of it's like social, cultural, IP issues that the companies that are doing it are not as interested in fixing them to get them in outer space. And that the market just isn't there, and they're already relatively expensive, and it's a small market. And so the way that they're designed just doesn't lend itself towards being hardened for outer space. They do sell some things that are already hardened, though that doesn't prevent people from trying to send them into outer space. FPGAs are actually really relevant for building radios, because it turns out that a lot of military contractors, instead of building custom chips, because if I'm only going to deploy 5 radars ever, I shouldn't build custom chips, because I need to at least build 1,000 to get my money back from tooling the foundry to build them. So I'm going to do FPGAs. And so what I might do is build huge arrays of FPGAs to do all of the processing. So I think Dan Bliss had a project where he had something like 20 FPGAs ganged together for a radar. So yeah, they're pretty important. A lot of our early prototyping we're doing on this radio project is on an FPGA.
And who's running this project?
What's that?
Who's running this project?
So Dan Bliss is in charge of the overall project where we're working on radios. My area is managed by Dr. Chakrabarty. And then I'm not doing much work. I'm just yelling at some of the students doing the work. I do math, and then I look at things and go, hey, we could do better. Cool. Anything else? All right. Thank you very much.